Try again. This is the next video for the Year 1 Pure. We're looking at the second of the two exercises on proof, working towards 7E. And as I said, it's an odd one, is proof. Proof by exhaustion means try all the different possible numbers. So depending on the problem, we can try even numbers and odd numbers separately. And that's usually what we do for proof by exhaustion. In fact, example 12 says this: prove that all square numbers are either a multiple of 4 or a multiple of 4 plus 1. It doesn't say it quite like that. One more than a multiple of 4 is actually what it says. So of course, if I want a multiple of 4, I need to write that in the form 4 times something, and a multiple of 4 plus 1, I need to write that in the form 4 times something, add 1. Okay, so let's consider odd numbers. So odd numbers, think back to GCSE. Odd numbers are going to be of the form 2n add 1, because 2n, 2 times anything is even, and add 1 is going to be odd. So this is any odd number squared. So 2n plus 1 is any or even every odd number. 2n plus 1 squared, if I multiplied that bracket out, I'd get 4n squared plus 4n plus 1, which of course I could write as 4 times n squared plus n plus 1. Well, this is a multiple of 4 because it's 4 times some expression in n, and of course this is definitely going to give me a whole number because n is an integer. Plus 1, which is, this is 1 more than a multiple of 4. If we consider even numbers, well, here it is, that's any or every even number, and if I square it I get 4n squared, which is clearly a multiple of 4. This is a multiple of 4. The last thing I write is what I was asked to prove. So since all numbers are odd or even, well, not numbers, integers, I guess, since all integers are odd or even, even, so all square numbers are either a multiple of 4 or one more than a multiple of 4. So proof by exhaustion, trying every different case. Sometimes a counterexample. Prove that a statement is not true by a counterexample. Prove not true the sum of two consecutive prime numbers is always even. I mean, the obvious one is 2 plus 3 equals 5. So the statement is not true. I only need one counterexample to show that the statement is not true. Okay, example 14 is an interesting one. Prove for positive x and y that this is true. Okay, now the way to prove this is through an algebraic method, through showing logical steps that can't be argued with and get a conclusion that can't be argued with. When I do a proof, what I want to try to prove, I want that to be the last thing that I say. So, before I attempt my proof, I'm just going to do a little bit of working out and having a think about it, and I'm going to explain my thinking as I go. Not a lot that I can do here other than turn it into a single fraction. If I multiply through, now this is only true because xy is positive. Think back to your inequality work that we've done. If xy were negative, then this would not be true because I'd have to flip that sign round. So this is only true for positive xy. X squared add y squared minus 2xy greater or equal 0. And if I write it like that, x squared minus 2xy minus plus y squared greater or equal to 0. Now this is a perfect square. You need to be able to see these sorts of things. This factorises to x minus y squared. Now this must be true. You cannot argue with this statement because anything squared is greater or equal to 0. So my proof actually is this in reverse. So what I say for my proof is consider this statement. This has to be true. You can't argue with this. This is a known fact. I'll expand it. Add that 2xy on. Nothing so far depends on it being positive. This next step will do though, won't it? For positive x and y, xy is positive, so that my next step is valid. X squared plus y squared over xy greater than or equal to 2. Then I can split this up into my original fractions. X over y plus y over x greater than or equal to 2. And there's my proof. So my working out, my thinking about it was, well, hang on a minute, what happens if I try to simplify this and get this quadratic? And that's what I did. Because that's true, I've used that as the starting point for my proof, because this needs to be the ending point for my proof. Part B says use a counterexample to show it's not true when x and y are not both positive. Well, you can do that yourself. You can put positive and negative x and y into that and see what happens. This is the difficult part, really. So this is my working out, I suppose. This is not really part of my proof. It's my thinking. But this left-hand side is my proof. And what happens is I start with a fact that you can't argue with. Each line is logically, is mathematically correct. There's nothing to argue with. Put a little bit of commentary in here to qualify this next statement, and then, well, these are mathematically equivalent, but I have to finish like that. I can't finish there. I want to finish like that because that's the statement that I'm trying to prove. Okay, have a go at 7E. Enjoy yourselves. Let me know if you need anything. See you later.